Hi, in this lesson we'll explore the remarkable limits. There are several remarkable limits. We'll consider two main ones. The first wonderful limit is the limit of the following kind. Limit as x tends to 0 the sine of x divided by x. It turns out such a limit is equal to 1. This can be strictly mathematically proven. The second wonderful limit is the limit of the following form. The limit as x tends to infinity. From such an expression, 1 plus 1 divided by x to the power of x. And again, it can be strictly mathematically proved that this expression is equal to the number e, the exponent. You have already encountered it as the base of the natural logarithm. This is an irrational number and approximately equal to 2.7, 1828, 1828, and so on. But in most cases, we won't use an approximation. We will just keep the letter e. It is also worth noting that the second remarkable limit helps us to reveal the indefiniteness of the form 1 to the power of infinity. That is, if we have such an indefiniteness, then most likely we need to apply this wonderful limit. Let's consider examples. Let's try to calculate the limits using the first wonderful limit. As a rule, the solution of such limits comes down to the fact that we reduce everything to a limit of this kind. Pay attention to the first wonderful limit. Despite the fact that we have x here and x here, x's don't have to be here. The main thing is that the expressions here and here are the same, tending to 0. And based on this, we can solve different examples. Let's consider this limit. Limit the tangent of x divided by x as x tends to 0. Here we use the trigonometric formula. Namely, we write the tangent as a sine divided by cosine. So it's the sine of x divided by the cosine of x. And don't forget the x from below. Now look, x tends to 0. We have the expression sine of x divided by x. This is nothing more than the first wonderful limit. That is, this value is equal to 1. Now we look at the cosine. Cosine of x when x is 0 is 1. 1 divided by 1 is 1. Thus we can use this formula right away. The tangent of x divided by x with x tending to 0 is equal to 1. Let's consider this example. In order to solve it, let's proceed as follows. Note that there is a tangent of 3x here. We already know that the tangent of x divided by x is also equal to 1 like our wonderful limit. That is, if there is x, then x should be also here. If there are 3x, then 3x are missing, and I should add 3x at the bottom. But I've added it just like that, so that nothing changes. I should add the same value on top. So far, nothing has changed. Sine of 2x, we have sine x divided by x. Here is sine of 2x, so 2x missed. I will add 2x above and 2x below. So far, nothing has changed. I can reduce 3x, reduce 2x, and get the initial expression. But we can see the following in this form. The tangent of 3x divided by 3x, it's likely the tangent of x divided by x. This is a wonderful limit and is equal to 1. The sine of 2x and 2x, even though this expression is reversed, this limit will still be equal to 1. It's like our wonderful limit. There are 3x left, divided by 2x, but we can reduce the x's, so there are 3 and 2 left. That is, this limit is equal to 3 seconds. That is, in fact, we are constantly adjusting to such a limit. Let's consider the following. In order to apply the first remarkable limit, we need to remember some trigonometric formulas. Namely, we write cosine of 6x as the cosine of a double angle. Cosine of a double angle is 1 minus 2 sine squared. 6x here. It means 3x here. Now, what do we get? Limit x tends to 0. On top there will be 1 minus 1, 0. Minus minus will give plus 2 sine squared, 3x. Below we have x sine 3x. We can reduce the sine squared, and the sine, it remains 2 sine 3x divided by x. In order to get a wonderful limit, we don't have 3x below. We don't have 3, so I will add 3 here. But since nothing changes, I will add it on top too. Now, the sine of 3x divided by 3x. That's 1. 1 remains, multiply by 2, multiply by 3. This limit is 6. And the last example. Here we have x tends to 0. X tends to 1. Write it down. In order to solve this example, we will leave the numerator unchanged. Sine 2, x minus 1, and factorize the denominator. That would be x minus 1, x minus 6. Now let's take a look here. With x tending to 1, the sine turns out to be equal to 0, so we can reduce it to the first wonderful limit. Here is 2x minus 1. Here is just x minus 1. There is lack of 2, so I'll just add it. Multiplied below, multiplied above, so that nothing changes. Now, this expression, this again the first wonderful limit, and it is equal to 1. It remains 2 divided by x minus 6. Substitute x equal to 1. 1 minus 6 minus 5 minus 2/5 in total. So you see that in order to use the first wonderful limit, we firstly need to remember some trigonometric formulas. And secondly, we are constantly adjusting to an expression of this kind. Now let's consider examples of the second remarkable limit. As in the case of the sine, x's don't have to be here. The main thing is that there and there should be the same expression tending to infinity. Generally speaking, if there is some expression that tends to 0, then there should be the same expression, but inverted. And when everything comes down to this kind, we can solve the limits for the second wonderful limit. I should remind you that the second wonderful limit helps us to reveal the indefiniteness of the form 1 to the power of infinity. That is, the first thing we check is whether we have a limit with such an indefiniteness. And if so, then we apply the second wonderful limit. Let's consider an example, checking the limit from this value, 3x plus 2 divided by 3x minus 1. If there would be no degree, then this limit would be equal to 1. 3 divided by 3 is 1, and there is really 1 to the power of infinity, so we can reduce it to such a limit. We need to take 1 and the remaining part. We'll proceed as follows to reduce 1. We'll write 2 as minus 1 plus 3. This will not change anything. Then 3x minus 1 by 3x minus 1, that's 1. That is, there will be a limit. X tends to infinity. 3x minus 1 divided by 3x minus 1 is 1 plus 3 divided by 3x minus 1. We got 1 plus some expression, which tends to 0. If x is infinity, then this expression tends to 0. Accordingly, there should be a power, the same but inverted. Therefore, we artificially add it. 3 divided by 3x minus 1 here, so we add 3x minus 1 divided by 3 here, but we have added this power just like that. Therefore, we need to reduce it. That is multiplied by the same expression, but inverted. Now I can reduce them, then nothing will change. And don't forget that there was the power, 4x minus 1. Now look. This expression, this is the exponent. That is, as we know, this value is equal to e. Indeed, we have this expression in the role of 1 by x. This expression plays the role of x. 1 plus 0 to the power of infinity. This is e. It remains to calculate this limit. We can do it very easily. We have 3 by 4 is 12x on top, 3x below. In the limit, it will be 12 divided by 3. That's 4. So it will be e to the power of 4. Let's consider the second example. 2x plus 1 divided by x minus 1. In the limit, it will be 2 by 2. 1 to the power of infinity. That is, we can fit it to the second wonderful limit. We need to highlight this one again. For this I will make 2x plus 1. I will write this plus 1 as minus 1 plus 2. Then there will be 2x minus 1 divided by 2x minus 1. That's 1. Plus 2 divided by 2x minus 1. So that this expression plays the role of 1 by x. This is 0, with x tending to infinity. Just like this is 0, then it must be to the power of x. That is this expression, but inverted. That is, I write 2x minus 1 divided by 2. I took this power just like that. Therefore, so nothing changes. Now I have to reduce it. Now, these degrees will be reduced. Nothing has changed. And don't forget about what we had. 3x plus 1 multiplied by 3x plus 1. Let me multiply it here. Now, look. This limit is equal to e. This is the second wonderful limit. It remains to calculate only this limit. Then it will be e, the power of this value. It's very simple. Open the brackets. There will be 6x plus 2 divided by 2x plus 1. In the limit, 6x by 2x is 3. In total, it will be e. This limit is 3, so e to the power of 3. We left it in this form. And let's consider the last example. Substitute x again. Infinity, x plus 2 by 2x plus 1. If we calculate the limit, it will be 1/2. 1/2 to the power of infinity. Pay attention. 1/2, and here is 1. That is, this is not a limit of this kind. We will not be able to reduce it to this form. Such limits are considered very simply, depending on whether x tends to plus infinity or minus infinity. We will get different solutions. If x is plus infinity, 1/2 to the power of plus infinity. That is 1/2 times 1/2, and so on, an infinite number of times. Then it will be 0. If x tends to minus infinity, then it will be minus infinity. 1/2 will turn over. There will be 2 to the power of infinity. It will be infinity. So, depending on where x tends to plus or minus, the solution will be either 0 or plus infinity. Thus be careful. We apply this limit only in situations where we get 1 to the power of infinity. If situation is different, we need a different solution. This video lesson is over.